Module 4, Lesson 1, the relationship of addition and subtraction. To be prepared for this lesson, you will want your workbook or the worksheets that go with the lesson. You will also want to have 10 squares of paper, all about the same size, so that you can do some modeling on your desk or on your table. I will try to pause at different intervals so that you know you can pause the video, and when you have completed the task, go ahead and unpause the video and continue. Here are your learning targets. Take a moment and read those through. And here is your I can statement for this particular lesson. I would like to draw attention to being very focused on addition and subtraction in this particular lesson. It talks about specific and general situations. Specific situations would be something like 2 plus 3. So we have specific values with which we are working. More general, something like a plus b, where we can choose a whole bunch of different values for a or b. So take a moment and use the squares that you've collected, and in your workbook, draw a tape diagram and represent 5 plus 4. Hopefully, add something like this. So you've got your 5, and then you've got your 4, and hopefully you are showing that you are combining them. All right, opening B here, go ahead and write an expression for each of the tape diagrams. Hopefully you were able to make a quick count here and have 2 and 2 more and 3 and 4 more. It's important that we recognize that these particular tape diagrams are showing that we are combining things. So pause for a moment and consider the following question. If each of the squares represents 1 unit, how would you represent the number 3 using your squares of paper? And how would you do that using a tape diagram? So if each square represents 1 unit, we would draw 3 squares because each square is representing 1 unit. So now we would add 2 more squares to our tape diagram. So we've got our original 3 here, and we've got 2 more. So how would we write an expression to represent what we just did with these squares of paper with this tape diagram? We've got our 5 pieces, we had our 3, and we added 2 more. So now remove 2 squares from the tape diagram and think about how you would write this as an expression. How would you show what you have done here? So here we have our original expression. We've got the 3 with the 2 more, 3 plus 2, but then we removed the 2, got rid of them. And so here I've used the image of actually crossing them out. And here is how we would show this mathematically. We're subtracting 2 off. So what is the value of our expression now? If we've got 3 and we added 2 and we took away 2, what do we have left? Well, we're right back to our original 3. So here's another one. This time create a tape diagram with 6 squares. There are the 6 squares. And now use your squares to demonstrate 6 plus 4. So we add on 4 more squares. Now stop and think for a moment. How would you label all this out? I like to communicate all this mathematically. So here is our 6, and here are the 4 more. So 6 plus 4. So now, how would we show removing 4? It'd be easy with your squares of paper. Just take the 4 squares of paper off. How would you represent this with a tape diagram? You could certainly X them out. And how would you show that mathematically? How would you show mathematically that you had removed 4? So go ahead and write that out. And here we have showing it mathematically. Notice that we have our original 6 plus 4, and we have added the minus 4. So how many squares are left on your desk? How many squares do you have left of your tape diagram? Hopefully you have 6. So if we were to evaluate the expression to show what we've actually got going on here, got our 6 plus 4 minus 4. And if we were to show our work, 6 plus 4 is our 10, and we subtract 4, and we are left with our 6. So how many squares did you start with? Hopefully you had 6. So here's a good thinking question. So definitely want to pause here and think about this. So what effect did adding 4 squares and then subtracting 4 squares have on the number of squares? What did that really do to everything? Well, adding and then subtracting the same number of squares didn't change anything. We ended up with the same number that we started with. So let's extend that thinking for a moment here. So if I asked you to add 215 squares to the 6 squares we started with, and then subtract the 215 squares, would you actually need to do that mathematically? Would you actually need to do 6 plus 215 and then subtract 215? Or do you already know what the result is going to be? And how do you know? And hopefully in your head you're like, no, I don't really have to do that. Because you know you're going to end up with the same number of squares that you started with. You added a number and you subtracted the same number out. So you'll have the original number. So here's a question. Looking at this generally, we've looked at a couple of specific examples now. Let's take a step out here, a step back, and ask ourselves, what do we notice in general? Well, when we add one number and we subtract the same number, we get our original number. Now we need to be asking ourselves, does this work every time? And how could we prove that that works every time? That's something we'll come back to a little bit later, like right now. So let's write an equation. So it's going to have an equal sign in it using variables that are going to show what we just demonstrated with the tape diagrams. So we're going to talk about this in a general sense. A specific example would be the first two examples that we've done. So for example, if we did 2 plus 3 minus 3, or 6 plus 4 minus 4, these are specific examples. So how can we write this out showing what is happening using variables? Well, one way we could do this would be w plus x minus the x. So this could be the 2 plus 3 minus 3. Remember, when we have variables, they represent the same number through the whole problem. So if this is 2, and this is 3, and this is 3, this has to be back to our 2. So why does this particular equation right here, why is that called an identity? Well, we have kind of a representation here of what's happening. We start with a number, we add something to it. So here's what we added. Then we turn around and we take that right back off. We delete it out, erase it, subtract it out. And when we're done, we're left with exactly what we started out with. If you stop and think about the identity problems that we use in math, like the identity property of addition, 2 added to nothing gives us 2. For multiplication, 2 times 1 would give us 2. 2 divided by 1 would still give us 2. And 2 minus 0 still gives us 2. So these identity properties, we perform the operations and we end up with exactly what we started with. There has been no change. So hopefully you can see that when we are adding the same number and then subtracting it back out, so like 2 plus 3, and we subtract that 3 right back out, we are right back to what we began with. There has been no change. So we call these identities because the variables can be replaced with any numbers, and after completing the operation, you return right back to the original value. Nothing has changed. So take a moment here and do some writing. Make a prediction what will happen when a tape diagram has a large number of squares. We take some squares away, and then we add back the same number of squares that we took away. So take a moment and predict that. So hopefully you have a prediction saying that when we take some away and then we add the same amount back, we get exactly what we started with. If I had 5 and I took away 3 and then I added 3, I end up with 5 again. Well, let's test this out on a couple of examples. So go ahead and build a tape diagram with 10 squares. And there are my 10 squares. Go ahead and remove 6 of the squares and write an expression to represent the tape diagram. So here are getting rid of 6. So I've got 10, and I took away 6. So now go ahead and add 6 more back on. So I'm just going to turn right around and put these back in here. 1, 2, 3, 4, 5, 6. Bring them back on. So then alter my original expression here, 10. That should be a minus. Quick correction here. So 10, took away 6, added 6 back in, and when I'm done evaluating, gee, I'm right back at the 10 that I started with. So we looked at this with a specific example. Now let's take a moment and ask ourselves, how could we do this with a general example? How could we do this with an equation? Well, the first one that we did, going back to our addition that we started with, we had a number, added another number, subtracted a number, and we're right back where we started. The second example that we looked at, we had a number, and we subtracted first, and then we added, and we were right back where we began. So here are some basic examples. This is the first problems that we looked at, where we added and then subtracted. Here's where we subtracted and then added. And these are both identities. We end with what we began with. Gone through all these different operations and come right back to where we started. So take a moment and in your workbook, using your knowledge of identity, fill in these blanks. What are the missing numbers? Well, I had 5 and I ended with 4, so I must have added off that 5, well, subtracted off the 5 that I added. Here we subtracted 10 and added 10. This must have been 45. And this must be 56. So taking a quick look here, I started with 4, I ended with 4, so I had to reverse that 5 off. Here was it added 5, so I subtracted the 5. Here I started with 25, ended with 25. I had added a 10 on, so this must have been subtracting 10. Here I've got a plus 16 minus 16. Those two are going to cancel each other out. So I've got a 45 and a 45. Here there's a minus 20 and a plus 20, so I must be right back here to this 56. So now we've looked at some specific examples. Take a moment and look at some general examples. So working with variables this time. All right, I added b, so I'm going to have to subtract b. I've subtracted d, added d, which means that all that will be left is the c. Started with e, ended with e. Here's a subtracting f, so I have to add an f on. And here I've subtracted an h, added an h, and I was left with a g, so I must be starting with a g. So now here is kind of a deep thinking question. Looking at these identities, when does it work? Is it always true? Does it only work sometimes? Does it work for all of the natural numbers, 1, 2, 3, 4, and 5? What about the whole numbers, our natural numbers plus 0? What about integers, positives and negative whole numbers? What about rational numbers, fractions and decimals? And how could you show and explain this to someone? So think deeply about that for a few minutes. Maybe even do some writing in your notebook. All right, so in every problem we did today, why did the final value of the expression equal the initial expression? Well, the overall change to the expression was 0. We subtracted 5, we added 5. This works very well with our additive inverses, our opposite numbers from Module 3. So initially, we added an amount and then subtracted the same amount. Later in the lesson, we subtracted an amount and then added the same amount. Did this alter the outcome? So remember, we added and then we subtracted and added. Did that change how things came out? No, it didn't change anything. In both cases, we still ended with the initial value. So why were we able to evaluate the final expression even when we did not know the amount that we were adding and subtracting? How were we able to find what we ended with even when we didn't know what we were adding and subtracting? Because if we add and subtract the same value, it is similar to adding a zero. They cancel each other out. -5 plus 5 gets us to 0. Remember that opposite number stuff that we worked on in Module 3. So here we go. Is it true? Does it work all the time? Does it work for all of these different kinds of numbers? And how do you know, and how could you prove it? Well, yes, it works all of the time. It works for natural numbers, whole numbers, integers, rational numbers. How do we know? Stop and think about what we learned in Module 3 with opposite numbers. They will add up or they will combine to make 0. Now, for proof, these different models that we have looked at are a great form of proof. So 3 plus 2, and then we subtract those out. So that's a specific example. So we could have A, and A represents some number, and we combine it with B. And if we turn around and take B off, we are right back to A. We could have A, and we could take off part of it that we could call B. And we could turn right around and put the B right back on there and be right back where we started out. So, as we reach the end of the lesson here, can you show and explain the relationship of addition and subtraction for specific and general situation? Can you show the relationship when you are given specific sets of numbers? Can you show with tape diagrams with various models? Can you show with variables, an A and a B? So in your learning targets, this lesson has been very focused on this first one right here. And we've also spent some time starting to think about some of these things, not quite as explicitly. So that concludes Module 4, Lesson 1. And feel free to repeat the video as many times as you need to. Make sure that you think your way through each of these problems. And if you have questions, be sure to ask them.